G'day chemistry students, welcome to another chemistry video. In this one we're going to be looking at dot point 2.1.2 and we're going to be looking at the concepts of stoichiometry and balancing chemical equations. Now I'm going to be showing you some work on some paper for most of this video, but to start off with, there's just a couple of slides to look at to sort of set the scene and get some of the main concepts through. So first off, what we're going to be looking at is the law of conservation of mass, and this is just a scientific rule that's been around for a good few hundred years now, and that is that mass, or in this case when we're looking at chemistry in particular, atoms, they can't be created or destroyed, and they can only be transformed from one into another. And when we're looking at chemical reactions in particular, what that means is that elements and atoms are forming bonds with new chemicals. We can't just magically get rid of a particular atom or reactant in a chemical equation. And so I guess what that kind of means here is, let's say that we were burning wood. A combustion reaction would mean that we'd have our fuel, in this case that would be the wood, and we'd be burning it with oxygen, and that would be forming ashes or carbon in some form, carbon dioxide gas and water vapor. And the idea of the law of conservation of mass would be that the wood and the oxygen, its mass put together, so all the wood that was originally there and all of the oxygen from the air that's been used to burn the wood, its mass all put together would be exactly the same as the mass of all of the ashes that formed, all of the carbon dioxide gas that formed, and all of the water vapor that formed. What you may have seen when you were doing some gravimetric analysis was that we can't always take these masses into account. Maybe some of that mass has been lost and wasn't captured in the container. Maybe some of it turned into a gas that or some of the products, were gases that were produced, and they escaped from the reaction vessel and can't be weighed at the end. Maybe the reaction had reactants, things that it reacted with that were gases to begin with as well, and they weren't even recorded by mass at the beginning of the experiment. But they all are there technically, and given perfect circumstances, we can in theory capture all of the reactants that we need, or capture all of the products that we get, and be able to get those masses measured completely, and those product and reactant masses, so the reactants on this side and the product masses on this side, would always be equal. So we have some examples here, and this is, I guess, this idea of stoichiometry and the balancing of equations. We're looking at reactions occurring in whole number ratios. So we're looking at applying the law of conservation of mass and its meaning to quantitative chemistry. What that means is, when we write a chemical equation, it's not really just enough to say that, let's say, hydrogen gas and oxygen gas react together to form water, because it doesn't tell us the entire story. If I were to remove these twos from my equation, what we would see is that we'd have a molecule with two hydrogens on it, a molecule with two oxygens on it, forming a molecule with two hydrogens and one oxygen. Now, those numbers don't balance out at all. And what that means is that either that mass has magically disappeared and is not accounted for, which doesn't really make sense with our law of conservation of mass, as we just talked about before. Look, it's potentially a possibility, but not one that happens in actual reality. What's actually happening is that these particles react and form products in different ratios. It's not just a simple matter of one molecule and one molecule makes another molecule in all circumstances. Certainly there are some that work in that ratio of 1 to 1 to 1, but that's certainly an exception to the rule, not the common occurrence. So in this case, you would need four hydrogens or two hydrogen molecules, four hydrogen atoms or two hydrogen molecules. You would need one oxygen molecule or two oxygen atoms to make two water molecules, which in total consist of four hydrogen atoms and two oxygen atoms. And the way that we show the number of molecules is by putting a large number out in front of the molecule. Now, keep in mind that numbers that are large and out the front of an atom or a molecule in a chemical formula, or a chemical equation, I should say, they are for the molecules themselves. So here I have two lots of H2. The subscript down the bottom is telling us the number of atoms present. So for H2, that means every molecule has two hydrogen atoms. Here there are two oxygen atoms in a molecule, and for this molecule of water, there are two hydrogen atoms, but only one oxygen atom. The subscript there specifically is for the atoms in the molecule. If we look at this guy over here, what we have is CH4 methane burning and reacting with oxygen to form carbon dioxide and water. Now, if you look and count up the number of carbons, the number of hydrogens, and the number of oxygens on both sides, what you'll find is they don't balance out. They don't equal the same amount. Without the numbers there, there'd be 1 carbon, 4 hydrogens, and 2 oxygens, whereas on the other side, there'd be 1 carbon, 3 oxygens, and 2 hydrogens. If we chuck extra molecules in, though, and end up balancing out the number of atoms, and what we have is a balanced chemical equation. I'm going to go through some techniques and some practice questions on paper in a second. So let's go over and do that. So in this first problem here, our 2 reactants are aluminium and chlorine gas, and they form an ionic compound called aluminium chloride. Now what we should notice straight away is that the aluminium atoms are balanced. There's 1 on each side of the equation. However, there are 2 chlorine atoms on the reactant side and 3 chlorine atoms on the product side. Now, we didn't make those chlorine atoms out of nothing, so what we have to try and do is balance out the equation so that there is an even number of aluminium and chlorine on either side. There's a couple of ways that you can go about this. There's one strategy that I'm going to use that's probably the most writing intensive or working out intensive, and I think it's a really good way to start approaching balancing equations questions, but certainly this is not something that you need to be doing all the time. Eventually, once you gain confidence in being able to balance equations in all circumstances, it really shouldn't be something that you'll have to do every single time, but certainly could be something to do while you're getting your head around how to balance these equations in the first instances as we are doing right now. And the way to do that is to write down each of the elements on both sides, make sort of like a column or a chart, I guess, for both sides of the equation, and actually count up how many atoms are on both sides. So on the first side, there's 1 aluminium and 2 chlorine atoms, and on the other side, there's 1 aluminium atom and 3 chlorine atoms. Now, what we need to do is increase the number of molecules, either of elements or of compounds, by whole numbers. And in doing so, you'll end up increasing the number of particles on either side of the equation, and you continue to do so until the whole equation is completely balanced out and there are the same number of each type of atom on both sides. So what we see here is that the aluminiums are currently balanced. There's nothing that we can do to balance them out anymore. But there are 2 chlorines here and 3 chlorines on the other side, on the product side. So what we can do is increase the number of chlorine molecules that I have here. So I have 2 Cl2s. So in total, that will mean that I have 4 chlorine atoms in total. So 4 on this side now, 3 on the other. Again, we're at a point of imbalance. So what I can be doing is increasing my number of chlorine atoms on my product side. So if I put a 2 out the front, I now have 2 lots of aluminium, or 2 aluminium atoms, and 6, double 3, 6 chlorine atoms as well. Now at this point, it may look like the numbers are getting further apart, but we're actually a lot closer than we were to begin with. Now what I see first is that we now have 2 aluminiums atoms on one side and 1 on the reactant side. I can double the number of aluminium that we have on the reactant side. That's quite easy. The aluminium's balanced again. Then what I can do is, instead of having 2 chlorine molecules, 2 Cl2s, I can have 3 instead, and that will get my total up to 6. So with all of that working, all that scratching, usually you would write out the balanced equation in full at the bottom with no working out or alterations or anything like that. And so what we're showing here is that we need 2 aluminium atoms, 3 chlorine molecules, or 3 Cl2 molecules to make, I've messed up my formula, to make 2 units of AlCl3. Now my second problem, following a similar set of steps, here I have C2H4, which is ethane. Oh, sorry, ethene, excuse me. Don't really need to know how to name them at the moment, but that's ethene. It reacts with oxygen gas, O2, and forms carbon dioxide and water. Now, if we draw up our chart, we're going to write down all of the types of elements that we have. So carbon, hydrogen, and oxygen on both sides. And what we're going to do is count them up. So there are 2 carbons currently on the reactant side, but only 1 carbon on the product side. We have 4 hydrogens on the reactant side, only 2 on the product side, and for oxygen, we have 2 and 3. So a clear imbalance of all of the elements that are present. Now, what we can do is make some adjustments to either side, and again, continue to make adjustments until we find something that balances them out. So speaking from experience, doing this lots and lots, I'm actually going to leave my oxygen until last. What I notice is that there is 1 molecule with just oxygen in it. There's 1 molecule out of all of these molecules, which is an element and not a compound. Elements are really good to leave to balance till last because you can just adjust them at the end and not change the number of other carbons or other hydrogens or any other element. You're just changing the number of oxygens if you leave it for the end. Hopefully that becomes a little bit more apparent as you do more practice questions, and maybe that might even make some sense by the time we get to the end of this balancing exercise. So what I'm going to do first is I can see that there are carbons and hydrogens that are currently unbalanced on this side. I can see that I need to double my number of carbons and hydrogens, so I'm going to do that at the same time. I'm going to have 2 carbon dioxides and 2 waters and do a full recount of all of my atoms on this side. So what I can see is that there are now 2 carbons. There are 2 lots of CO2, so 2 carbon atoms. For the hydrogens, there are 2 waters. So in total, there will be 4 hydrogen atoms all up. And then for oxygen, there's some coming from the carbon. So 2 lots of CO2 mean that there's 4 oxygens on all the carbon dioxides. And there are 2 oxygens in total for the 2 waters that are there. So that makes 6 in total. Now at this point, our carbons are balanced, our hydrogens are balanced, but our oxygens are not. But we have an excess on the product side, which means all we need to do is adjust the reactants. And thankfully, we have an element here, just oxygen by itself, that we can adjust instead. Now here we have to go up by 2, so I want 6 oxygens in total here. So that will mean I need 3 lots of O2. And that will mean that I then have 6 oxygens. And my equation is now balanced because I have 2 lots of carbon atoms, 4 lots of hydrogen atoms, and 6 lots of oxygen. Now, there are many different kinds of equations. Some are easier to balance than others. When we're in class, we'll be practicing a fair few in the period that we have to practice balancing equations, but this is an activity that you'll be completing throughout the entire course. So if you don't absolutely understand it inside and out the first time, there will be room for you to continue improving on this concept and these strategies as we move on throughout the year, but it is a fundamental part of our chemistry and something that we need to continue to work on. Now, as we move into our next video, what we're going to be looking at is the mole concept. Now, to keep it short, the mole is something that we can use to count the number of particles in all of our substances that we work with, which is an extremely powerful type of measurement to be using in chemistry, because a lot of the time, and we've already started to see this when we've been looking at our reaction equations recently, the number of particles a lot of the time is actually more important than any other kind of measurable metric that we can use. So things like volume and mass are significantly less important when explaining chemical reactions and how they work. The number of particles, as we can see, is a lot more important, and this is where the mole really comes into its own power. But until then, have a good one.